Good morning, friends. Welcome to Energy Engineering classes. I am V. Sushant Kumar. We are discussing Module 5, Biomass Energy. This is second class on biomass energy. In today's class, we'll discuss about digesters and what are the factors affecting the performance of digesters and the components of biogas plant and classification of biogas plants and working principles of all those types of biogas plants. Now let's look at what is digester and how it functions. So here you can see the sketch. So this is the digester and this is the mixing tank, and after the digestion, after the biogas formation, this is the collector, oxidation pond, so where the sludge is collected. The feed consists of organic material slurry prepared in mixing tank. So here, so we are going to prepare the organic material, and we supply this feed every day to the digester, and we call it as loading rate. So neither overloading nor underloading of the digester is desirable, as it reduces the biogas production. So there is a ratio for that. So we have to load the biogas digester accordingly. So there are two types of bacteria that work. One is acid forming bacteria, and second one is methane forming bacteria, which we call it as anaerobe. So acid forming bacteria, it grows rapidly, and whereas methane forming bacteria, it grows slowly. So to obtain maximum biogas generation, seeding of digestion slurry with methane forming bacteria is done. Means whatever slurry we are going to send to the digester, we are going to add methane forming bacteria, because it works slow. So how it is done? It is done by adding certain portion of digested slurry to the fresh slurry. So here we get digested slurry, and that slurry is again we are going to add some part of that to the fresh slurry. So that the methane forming bacteria is sufficient to form the biogas. So it is also possible, along with that, we can also add nutrients that contains nitrogen, hydrogen, oxygen, phosphorus, sulfur, and carbon, which can also increase the anaerobic digestion rate. The recommended pH value for the digestion of biomass slurry is about 7 to 8. So this is how the digester functions. So in the upcoming slides, we will discuss in detail about this digester. Now let's look at the factors that affect the performance of digester. First one is temperature. So bacteria grow and work best in the temperature range of 20 to 65 degrees Celsius. So it is very important that we maintain the temperature range between this. And second is the pressure. So we have to maintain a pressure of 6 to 10 centimeter of water column. It is considered ideal for proper functioning of digester. And third one is water. The presence of water helps in better mixing of various constituents of the biomass and hydrolysis of biomass, and it also helps in movement of bacteria and faster digestion process. So the optimum solid content of the biomass is about 9 to 10%. And fourth one is pH value. The pH value in the acid forming stage of the digestion process, it should be around 6 acidic. So but during methane forming stage, the pH value should be about 6.5 to 7.5, as the anaerobic bacteria do not grow in acidic solution. And next one is feeding rate. A uniform feeding rate should be maintained. In case of faster feed, means if you supply the fresh slurry fast into the digester, acids will accumulate to stop the digestion process. In case of slow feed, the digestion process slows due to non-availability of sufficient biomass. So we have to make sure that the feeding to the digester is uniform, and it should be daily. And the next one is presence of nutrients, carbon, nitrogen, and other nutrients are essentially for digestion. So next one is seeding. To start or accelerate the digestion process, it is customary to add a small amount of digested slurry containing methane forming bacteria to the freshly charged digester. This process is called seeding of bacteria. So as we discussed, methane forming bacteria, they work slowly, so we need to accelerate the reaction since they work slowly. So what it is done is, whatever digested slurry that comes out, some part of that is added to the fresh slurry that is sent to the digester. So this process we call it as seeding. And next one is mixing and stirring. Mixing and stirring of digester slurry, it helps to mix the floating masses of biomass in the slurry for bacterial action, so as to speed up the methane forming process in the slurry. And next factor is retention time. It is the duration for which the biomass slurry remains in the digester. The digesters are designed to keep the biomass for a retention period ranging from 30 to 50 days, depending on the region and the type of biomass. So retention time is optimized to get at least 70 to 80% of digestion of slurry. Next one is toxic substances. Next factor, the presence of pesticides, detergents, and ammonia in the biomass affects the digestion process. So we have to make sure that we don't add these pesticides, detergents, and then the material content that contains ammonia. And the last one is the type of biomass. The digestion process also depends on the type of biomass that we add into the digester. The biomass can be cow dung, poultry manure, sheep manure, night soil, rice husk, algae, water hyacinth, and these have a different rate of biogas yield per unit mass. So based on all this, the digester biogas plant is designed, and these are the factors that affect the performance of digester. Now let's look at the components of biogas plant. So this is mixing tank, so where we mix the biomass, and this is the inlet pipe, and this is the digester. So you can see this structure with which is constructed with bricks. So this is the digester. So it is also called as a fermentation tank. It is embedded partly or fully in the ground. It is generally cylindrical in shape, and it is made of bricks. So it holds the slurry for sufficiently long time to complete the digestion process. So on this you can find a dome-like structure, this dome-like structure. So this we call it as gas holder. So the function of this is to keep the gas, and for subsequent use we have the outlet pipe. And next we have outlet pipe, and this is overflow tank. Means once the digestion takes place, the sludge gets collected here, and it also contains a stirrer. So it's not shown in the sketch, but it contains a stirrer for mixing of floating slurry for better reaction. So these are the main components of biogas plant. Now let's look at the classification of biogas plants. The biogas plants are mainly classified into four types. So first one is batch type of biogas plant, and second one is a continuous type biogas plant, and third one is floating drum type biogas plant, and last one is fixed dome biogas plant. So we'll discuss in detail about all these types of plants. In batch type of biogas plant, we have more than one digesters, and whose floating tanks are connected, as you can see from the sketch. So these are the digesters, and they are connected, and the biogas is stored in a common tank for the use. So this type of arrangement we call them as batch type of biogas plant. So uh, it consists of number of digesters which are charged, used, and emptied one by one in a synchronous manner to maintain a regular supply to gas holder or storage tank. Each digester is charged with fresh biomass, and it starts supplying biogas after 8 to 10 days. The digester is now capable of supplying biogas for about 40 to 50 days till its biomass is completely digested. Afterwards, this digester is emptied and recharged with fresh biomass. Hence, each digester should be charged in about at interval of 50 to 60 days. So we have to maintain the charging feeding rate. We have to plan it so that we get the biogas continuously from all these digesters. So this is about batch type of biogas plant. So second type of biogas plant is the continuous type of biogas plant. So in this type of biogas plant, certain quantity of biomass slurry is fed daily into the digester. This is made possible by the removal of digested slurry through an outlet, so that the digester can have space to intake fresh biomass slurry. So the biogas produced is either stored in the digester or removed to be stored in a gas holder. The plant operates continuously, and it is stopped only for the removal of sludge. The layer of scum at the top of biomass slurry is periodically broken with the help of stirrer. The stirring also helps in better mixing of the biomass. You can just go through the sketch here. So this type of plant is most suitable for individual houses, as the daily wastage can meet the biomass feed requirement for the digester. So in most of the houses, they go for the continuous feed type of biogas plant. Next one is floating drum type biogas plant. You can see from the sketch, and already this sketch we discussed previously. So we have inlet mixing tank here. This is the overflow tank, means where the digester slurry gets collected, and this is the digester, and this is the gas holder. So the plant consists of an inverted metallic drum to function as gas holder, and an underground digester constructed from the masonry with a partition wall as shown in the figure. So here you can see, so here we have a partition, okay, for the smooth movement of the slurry. The digester chamber is provided with a partition wall at the center so that optimum conditions for the growth of acid forming bacteria and methane forming bacteria can be provided in the partition portions, as biomass slurry should be acidic and basic for acid forming and methane forming bacteria respectively. The pipe arrangements are provided to the digester for the supply of fresh feed of biomass slurry and removal of digester slurry. So as the digester has floating gas holder, you can see this is the floating gas holder. The pressure inside the digester remains constant. Means if the production of gas is more, then the floating gas holder it moves up, and if the production of gas is less, the floating gas moves down. It is free to float. It's free to move up and down, so that the pressure inside is constant. So one advantage of this is there is no risk of explosion due to change in pressure of the gas. This is about floating drum type biogas plant. So type of biogas plant is fixed dome type of biogas plant. So in the previous slide we discussed about floating dome type. So in floating dome, the pressure is kept constant but the volume varies. In this type of plant, so the volume is fixed. You can see from the sketch. So here we have a dome which is constructed from the bricks masonry. So the volume is fixed but the pressure variation takes place. Okay, so the difference between this and that is there we have floating dome where the gas is collected, and here it is the dome is fixed. So it has a constant volume but varying pressure inside the digester, as it has no movable type of gas holder but a fixed dome at the upper portion of the digester, as you can see from the sketch. The biomass and water are mixed into slurry in the inlet tank here. So this is the inlet tank, so which is fed into the digester through the inlet pipe. So this is the inlet pipe. A stirrer is provided, so you can see this is the stirrer. A stirrer is provided in the digester tank to mix the slurry inside the digester. So it also helps in mixing of scum floating on the slurry. The generated biogas accumulates in the fixed dome. So here the whatever biogas that is formed, it gets accumulated here, fixed dome, and the residual digester slurry is taken out from an opening in the digester in the modified fixed dome. So this is the collecting tank, and as the biogas production takes place, so the pressure increases. So once the pressure increases, so it applies force on the slurry. So as a result, the slurry moves up and the level increases. So this is about fixed dome type of biogas plant. Now let's look at the application of biogas in IC engine. So the properties of biogas are composition. Methane is about 60% and carbon dioxide is about 40%, and along with that we also have traces of hydrogen, hydrogen sulfide, and other gases. And its calorific value is about 5160 kilocalories per meter cube, or we can convert in terms of kg, 4250 kilocalories per kg. And stoichiometric air fuel ratio is about 5.27 by volume, and the calorific value of the mixture is about 767 kilocalories per meter cube, that is about 85% of gasoline. So we cannot directly use this biogas directly into the IC engine. Some modification has to be carried out in the IC engine to use this biogas. But however, with blending of biogas in small amount with both petrol and diesel, it is possible to run IC engine by it with a small modification, providing gas kit and supply system. It is found that mixture of biogas and gasoline containing 5 to 10% biogas can be successfully used in IC engine fuel, thereby reducing the limited and costly gasoline consumption by 5 to 10%, and at the same time by reducing the cost of the fuel. Now let us discuss a new topic: urban waste to energy conversion. So what is urban waste? Urban waste can be defined as the waste collected from residential and industrial areas of the cities and towns. So around the world, the waste generation rate is rising. So as per the 2016 data, the world's cities generated about 2.1 billion tons of solid waste, amounting to a footprint of 0.74 kilograms per person per day. So with this rapid population growth and urbanization, so annual waste generation is expected to increase by 70% from 2016 to 3.4 billion tons in 2050. So the dense population in urban areas produce the enormous amount of waste. So highly populated areas require efficient waste management systems, so that manage the process of collection, transportation, recycling, and disposal. So proper waste disposal and poorly managed landfills generate ground and air pollution, so that has harmful effects on the people and the environment. So modern innovations can help cities protect the health and safety of their citizens while cutting overall costs and conserving resources. So managing waste properly is essential for building sustainable and livable cities. But it remains a challenge for many developing countries and cities. Effective waste management is expensive. It often comprising of 20 to 50% of municipal budgets. So operating this essential municipal service requires integrated systems that are efficient, sustainable, and socially supported. Waste to energy conversion is the process of generating energy either in the form of electricity or and heat from the primary treatment of waste or the processing of waste into a fuel source. Processes generate electricity and or heat directly through the combustion, or produce a combustible fuel commodity such as methane, methanol, ethanol, or synthetic fuels. So what are the methods that are used to convert the waste into energy? So I have listed out few methods here, like incineration, gasification, thermal depolymerization, pyrolysis, plasma arc gasification, anaerobic digestion, and fermentation. So we will look into these in upcoming slides. Let us study the first method of converting waste into energy, that is incineration. Incineration is waste treatment process that involves the combustion of organic substance that is contained in waste material. Incineration of waste material converts the waste into ash, flue gas, and heat. So it generally entails burning of waste like municipal solid waste, commercial waste, industrial waste, and refused derived fuel RDF. Okay, so we use this waste, we burn this to boil water, so which powers the steam generator, and that generate the electric energy and heat to be used in homes, business, institutions, and industries. So incinerators have an electric efficiency of about 14 to 28 percentage. So they reduce solid mass of original waste by 80 to 85%, and by volume by 95 to 96%. They also emit fine particulate matters, heavy metals, trace of dioxin, and acid gas, even though these emissions are relatively low. So this is about incineration method. Second type of energy conversion from the waste is gasification. So it is a process that converts biomass or fossil fuel based carbonaceous materials into carbon monoxide, hydrogen, and carbon dioxide. So this is achieved by reacting material at high temperature, around more than 700 degrees Celsius, without combustion, with a controlled amount of oxygen or steam. So the resulting gas mixture, we call it as syngas or synthesis gas. It is also called as producer gas, and is itself a fuel. It can be used as a fuel. The power derived from gasification and combustion of resultant gas is considered to be a source of renewable energy if the gasified compounds were obtained from the biomass. The advantage of gasification is that using this synthesis gas, it is potentially more efficient than the direct combustion of original fuel, because it can be combusted at higher temperatures or even in fuel cells, so that the thermodynamic upper limit of the efficiency defined by the Carnot rule is higher. So basically what I mean to say is the efficiency of using the synthesis gas is higher than the burning the fuel directly. So synthesis gas or syngas may be burned directly in gas turbines used to produce methanol and hydrogen, or it is converted via Fischer-Tropsch process into synthetic fuel. So for some materials, gasification can be an alternative to landfilling and incineration. Some gasification process aims at refining out the corrosive ash elements such as chloride and potassium, so allowing clean gas production from otherwise problematic fuels. So gasification of fossil fuels is widely used currently on industrial scales to generate electricity. So gasification can generate lower amounts of small pollutants such as sulfur oxides, nitrogen oxides than combustion. Next process is thermal depolarization process. It's also called as TDP process. So in this process, it uses hydrous pyrolysis for the reduction of complex organic materials. So complex organic materials means here is waste products like biomass, plastics, and it converts into light crude oil. So under pressure and heat, the long chain polymers of hydrogen, oxygen, and the carbon, they decompose into short chain petroleum hydrocarbons with a maximum length of around 18 carbons. So you can just go through the table here. So by using this TDP process, uh, we get various products from this. Like if you use TDP process for plastic bottles, we get oils around 70%, gas around 16%, and solids mostly carbon based around 6%, and water around 8%. So in this fashion, we have listed a few urban waste and converting that into small chain petroleum hydrocarbons, and we get various products. You can just go through the tabular column here. Next type of waste to energy conversion process is plasma gasification. Plasma gasification is an extreme thermal process using plasma, which converts organic matter into syngas or synthesis gas, which is primarily made up of hydrogen and carbon monoxide. So there will be a plasma torch which is powered by electric arc, which uses the ionized gas, and it catalyzes organic matter into syngas with slag remaining as byproduct. So it is used commercially as a form of waste treatment, and has been tested for the gasification of refused derived fuel, biomass, industrial waste, hazardous waste, and solid hydrocarbons such as coal, oil, sand, petcokes, and oil shale. So small plasma torch typically use an inert gas such as argon, where large torches require nitrogen, and the electrodes that are used, they vary from copper to tungsten or hafnium to zirconium, along with other alloys, and a strong electric current under high voltage passes between these two electrodes as an electric arc. So pressurized inert gas is ionized, passing through the plasma created by the arc. The temperature varies between 2000 to 14,000 degrees Celsius. The temperature of plasma reaction determines the structure of the plasma and forming the gas. By this way, we get synthesis gas, so which contains carbon monoxide and hydrogen. So the high temperature and lack of oxygen prevents the formation of toxic compounds such as fuels, dioxins, nitrogen oxides, and sulfur oxides. So these are the different methods which helps in converting the urban waste into useful energy. So in today's class, we discussed about digesters, and what are the factors affecting the performance digesters, and what are the components of biogas plants, and how the biogas plants are classified. And we also discussed about interesting topic, what is urban waste management, and how to convert this waste into useful energy. So what are the different methods and how they work? If you have any doubts, feel free to contact me, and thank you for watching the video.